Hello, everyone. My name is Xijun Shi. I go by Jeff. I'm an assistant professor at Texas State University. It's a great honor to present our work here at the ACI convention. My presentation topic today is long-term evaluation of concrete pavements containing recycled concrete aggregate in Oklahoma. I want to note that this presentation is based on the project that we completed for Oklahoma DOT, and the work was done when I was a PhD student at Texas A&M University. And my co-author is Dr. Anil Mukhopadhyay. He's a project PI, and he's also my PhD dissertation co-chair, and my dissertation chair is Dr. Dan Zollinger from Texas A&M University. All right, so let's move on. Okay, let's see. Okay, so the topic is related to use recycled concrete aggregates from older pavements to make new pavements. So why do we recycle concrete pavements? There are a number of benefits we can achieve. By recycling concrete pavements, we will have economic benefits. So we all know in a typical concrete pavement, construction aggregate cost is around 20 to 30% of the material cost. And we also know the virgin aggregate cost is increasing due to many factors such as scarcity of the virgin aggregate source, concern about environmental pollutions, zoning issues, and also increased the haul distance between those aggregate supplies and the ready-mix concrete plants. On the other hand, we know our US highway systems were established a few decades ago. Many roadways have shown severe distresses and need maintenance and rehabilitation. If we do not recycle pavements, the construction waste needs to be landfilled. Here I'm showing some statistics. According to National Solid Waste Management Association, the landfill tipping fees have been increasing dramatically during the past few decades. So by recycling concrete pavements, we can also achieve environmental benefits. So we know our nature resources are reducing very fast. Using recycled aggregates can mitigate further consumption of our nature aggregates. And with less virgin aggregates being mined, we can save energy and we can emit less greenhouse gases. And also landfilling and stockpiling construction waste pose a threat to the environment and also the public safety. So by using recycled concrete aggregates, we can help dispose of these waste and we can reduce the negative impact to our environment. However, the use of recycled concrete aggregate in pavement applications has not been widely accepted by a lot of states. Based on a recent survey, we're just showing some examples here. Texas, Colorado, and Alabama allows to use RCA in concrete pavement slabs. Michigan allows for temporary payments and also some low strength applications. Virginia does not allow to use RCA in reinforced concrete because they were worried about the chloride content in RCA. And Florida only uses RCA for base or to stabilize on the subgrade. Again, these are some samples. There are many other examples probably we haven't learned about yet. And we know lots of researchers, scholars around the world, they did lots of lab tests. And we all know the addition of RCA into concrete could change concrete properties very significantly. And based on our literature review, based on the lab studies, here we summarize the effect of RCA on concrete properties. By adding RCA, the effect on slump actually can either be improved or decreased. So it really depends on the mixed design and also RCA quality. And by adding RCA, we are likely to have higher L content in the new RCA concrete. And by adding RCA, the concrete abrasion resistant tensile strength, compressive strength, MOE, fracture strength, and the carbonation resistance will be decreased. And also for the drying shrinkage, creep, cholera penetration, and thermal expansion will be increased by using RCA. So the major work we did for the Oklahoma DOT was to inspect the field conditions of 2 existing RCA concrete pavements in Oklahoma. Unlike lab studies, field studies of RCA concrete pavements are rare in the United States. Especially for our study, we will focus on long-term performance of RCA concrete pavements. A little bit background, Oklahoma DOT built several sections of concrete pavements containing 100% coarse RCA in the 1980s, and we were able to inspect JPCP section and CRCP section in Oklahoma City. And as far as we know, those sections have never been extensively evaluated before our study. And because those pavements were built in the 1980s, it was a unique opportunities for us to see the long-term performance of RCA concrete pavements in the United States. So in this table, as you can see, we have 2 sections. One section, it is JPCP section. It is located on I-40 near Oklahoma City, and the length is about 7 to 7.5 miles. And the original pavement, I mean, the RCA concrete pavement was built in 1983. We had 10-inch slabs containing 100% coarse aggregate, coarse RCA, and we also have control section, which is on the same pavement. And the base for the I-40 is soil asphalt, and it is 6-inch. And we also have our CRCP section located on I-35. It is around like 6 miles, and it was built in 1989. And the slab thickness was also 10-inch. And we also had both control and the RCA concrete pavements for us to compare with. And the sub-base for the CRCP RCA concrete pavements was 4-inch asphalt concrete sub-base. We also look at some literature review. We also talked to people nearby, and we learned some stories about those 2 existing RCA concrete pavements. So for the I-40 JPCP section, so the motivation back in 1980s was that the contracts really could not find a very nearby quarry which can supply virgin aggregates. So therefore, they decide to use recycled concrete aggregates from the old pavements, and it ended up they saved about 63,000 tons of virgin aggregate, and then they saved about $4.8 million back to that time. And the project started on March 10, 1983, and it was finished in around 8 months. And the contract was able to produce satisfied Class A concrete with 100% coarse RCA replacement. And the old concrete, which they recycled those RCA from, had more than 20 years surface life. And the major problem was with the old pavement was the pavement showed a severe decracking issue, and so to mitigate decracking issue from happening, the contract decided to use smaller size aggregate for the newly built RCA concrete pavement. And for the I-35, we did not find a lot of information compared to the I-40 case, but we know the old concrete which supplied the RCA was built in 1960s, and the new RCA concrete pavement was contracted in April 1988, And Oklahoma's DOT actually had a chance to go back to the I-35 CRCP sections 22 years after 1982. So it's at like beginning of 2000. And they did not identify any distress. So in the summer of 2017, Dr. Mukhopadhyay, Dr. Zollinger, and we went to Oklahoma City for the pavement inspections. We did a visual inspection. We found there was a significant amount of longitudinal cracks on I-40, which is JPCP section. We did not find any decracking issues. Remember, I-40 was reconstructed due to decracking issue in the 1980s. And for the CRCP I-35, the pavement looked very good. And we also were able to core some specimen from the fields. And we confirmed that for the I-40, it was asphalt treated soil base. And it appeared that the base was very weak. And for the I-35, we found it was actually asphalt pavements, asphalt concrete. And we found the asphalt concrete base was very strong. So as you can see on the picture here, you can see we were able to extract a specimen which base and the slab was not detached, was still attached to each other. Then we did a FWD falling weight deflectometer testing there. So we look at 4 major parameters for the concrete pavement structures. We developed some theories behind to evaluate base erosion use FWD results. So those 4 parameters we will look at it was equivalent thickness, which consider both base and concrete slab, and also considers a bonding between those 2 slabs. We also look at the base coefficient friction. As I mentioned, we had a theory that calculates those coefficients. We also calculate differential energy using the pavement ME equations. And we also look at load transfer efficiencies. There are lots of theories behind lots of equations. I'm not going to go over them today. If you are interested, you can find those equations in our TR paper, which I will list it at the end of the presentation. So for the results, we found for the I-40 JPCP, the RCA section had a lower performance than the control section, which did not have any RCA. And we found it has lower equivalent thickness for the RCA section. It has lower base coefficient friction, and it also has higher differential energy. For the CRCP, however, the RCA section and the control section had a very similar performance. We had a similar equivalent thickness and a base coefficient friction, but for the differential energy was higher for the RCA. Actually, higher differential energy makes sense because RCA concrete slab has lower modulus, so you have higher deflection, then you will have higher deflection energy. We also had a chance to have some distress survey results provided by Oklahoma DOT. The data was collected on July 10th, 2016, about 1 year before we visited the site. And the results was consistent with our field inspection. And for the JPCP RCA section, it had lower performance. It has higher IRA, International Roughness Index. For the RCA, had a higher than the control. And for the RCA concrete, it also had higher faulting value compared to the control. For the CRCP located on I-35, the performance was very similar between RCA and the control sections. The IRR value was close. The control section had a higher patching area, but for the RCA section had a higher amount of punch out. So we consider they had a similar performance on the I-35 for the CRCP sections. We also did mechanical properties for our course from the field. For the major conclusions are RCA concrete has lower modulus elasticity and also lower split tensile strength. For the RCA concrete, on the I-40, it had higher compressive strength, but we reported a lower value for the I-35 compared to the control. This is interesting. And we also did some petrographic study. We used a thin section to see the reclaimed mortar, which you can see on the graph here. You can clearly see the reclaimed mortar. Then we also introduced some cracking in the core we took from the field. Then we found the cracking actually passed through the reclaimed mortar. So we can conclude that the reclaimed mortar is a weak zone in this system. So there are some key findings from Oklahoma concrete pavements. For the RCA concrete, we had a reduced modulus elasticity and the tensile strength, but we did find an increase in compressive strength on I-40. And for the reclaimed mortar, we found it is a primary weak zone and the crack can easily pass through. And for the field studies, we found the JPCP section, RCA section had a lower performance, but for the CRCP, the performance was similar to the control. And we believe the good performance of the RCA CRCP was because of the stronger base. Remember, it was built on asphalt concrete base, which was very strong, but for the other one, which was built on asphalt treated soil base, which was not that strong. And also we thought the inherent stiffness of CRCP can help protect the base from erosion. I actually have a few more slides, but I probably running out of time. So we also did some literature review. We found there are a few existing studies related to the RCA field studies in the United States. For example, FHWA had a few studies in 1994 and 2006. They evaluate a lot of existing concrete pavements in the United States in different states. And some of the concrete pavements were JRCP, some of them are JPCP, and even we had a CRCP. And we also have sections used to find RCA along with the coarse RCA replacement. So if you are interested, you can find some 2 TRR papers here. And we also have RCA CRCP studies, which was reported before. For example, we had Textile had an existing RCA CRCP studies. So in 1995, Textile reconstructed IH40 in Houston, and they used 100% coarse aggregate RCA and coarse fine and 100% fine RCA to replace coarse aggregate and fine aggregate respectively. And after 5 years construction, Dr. Mu Wang from Texas Tech University, they visited the site, and they had some they had a report. And so the major findings were the contracts noticed that the moisture control of the RCA stockpile was very crucial, because if we do not control the moisture content of the RCA, then the consistency of the RCA concrete will be very bad. They were able to use normal paving operations to construct those RCA concrete pavements. And for the district survey, no districts were found. The transverse cracking spacing distribution was comparable to the control, and they did not find the older mortar had a significant negative effects. And also Dr. Rossler from University of Illinois, they also did a field study on existing CRCP concrete on I-55. And 20 years after constructions, they did some field studies. They also did a FWD test. They found those CRCP RCA sections had excellent load carrying capacity and load transfer efficiency. And for the distress surveys, they found there are a few longitudinal cracks on the RCA sections, and they conclude that it might be sediment cracking due to the reinforced rebars. And also, they did not find an ASR problems, and the elbow system of the CRCP RCA section was great. And they did find shorter transverse cracking, and it was primarily due to greater drying shrinkage potential of RCA concrete, and also the lower tensile strength, and also reduced fracture properties of the RCA concrete. For the skid resistance, they found it was satisfactory, and also they reported fail to good ride quality of the RCA concrete pavement.
Hi, Jeff. Sorry to interrupt you. Can we wrap it up? Yeah, this is the last slide, right? Because we have the 5th presenter here, actually.
Oh, okay. Yeah.
Sorry about that.
Sorry. Okay, this is my last slide. So there are some conclusions. We want to remove reclaim mortar as much as possible. We can use the impact on cone crashes. We want to control the stockpiles, and some people suggest washing aggregates maybe can be helpful to remove cholera and fines. And we also need to evaluate the existing distress from the old concrete. And typically we can allow 100% coarse RCA in concrete pavement. In some states like Texas, we allow 30% fine RCA. And workability, we can use some strategies to improve the workability, and we can also use more cementitious material to improve the stress. Acknowledgement, I want to thank Oklahoma DOT and my supervisors and my colleagues. And I also want to thank lots of experts who helped us during this project. Thank you, and I'm listening to relevant publications related to this study. Thank you so much.